Assalamualaikum warahmatullahi wabarakatuh, and good day everyone. In this video, I'm going to discuss with you two questions related to soil strength. This is a topic on the soil mechanics course for students year 1 University Technology Malaysia. So in this video, the questions will be provided also with solutions, okay, respectively. Here are some important equations that can be used in order to solve the questions regarding to strength, shear strength specifically. So if you look at the list given here, we have the Mohr-Coulomb equations, okay, in which that shear strength will be equal to coefficients plus normal stress multiplied by tangent friction angle. Remember, two main parameters of shear strength are coefficients and friction angle. But bear in mind, as we discussed, not necessary that type of soil will have both parameters. If cohesive soil, okay, it's been considered, it means that the shear strength would be relies on coefficients, in which that the friction angle would be assumed to be 0. On the other hand, if the type of soil is coefficient soil, means that the shear strength will be depends mainly on friction angle, in which that C will be assumed equal to 0. In addition to that, we also have failure angle, okay, represented by theta, can be also determined based on these equations, okay, with the relationship of friction angle. So theta can be calculated equal to 45 plus friction angle divided by 2. The same thing also, if you know the value of theta, to find the friction angle, you can also use this similar equation. For shear stress at failure, you can use these equations, okay, where you need to also to know the major principal stress and also minor principal stress together with a failure angle value. For normal stress corresponding to shear stress at failure, you can use either these equations or these equations. And this equation is actually been derived, okay, by combining, okay, the equations of normal stress and also shear stress at failure into the Mohr-Coulomb equation, into these equations. So by solving, okay, the two equations, this with this or either this, into these equations, you will get this long equations, okay, where you can find out the major principal stress value, okay, with whatever parameters, okay, given that suit to these equations. And similarly, if the soil is coefficient soil, in which that the C value will be equal to 0, that means that to calculate the major principal stress of respective type of soil, the equations will only limit to here, okay, because C is equal to 0, so you can cancel out, okay, this part. Okay, let's look at the first example here. Okay, first of all, you need to understand the equations. The equations given are a soil field at minor principal stress, okay, or also known as confining pressure, okay, some reference put denote as sigma C, which is similar to sigma 3, a minor principal stress, also known as cell pressure or confining pressure, which is equal to 100 kilonewton per meter square, okay, and sigma 1 equal to 288 kilonewton per meter square. So sigma 1 is major principal stress, okay. If the same soil is given, okay, it means that you prepare identical specimens but subjected to a different minor principal stress or confining pressure of 200 kPa or kilonewton per meter square, what is the value of the new sigma 1? Okay, you are referring to the specimens with 200 kilonewton per meter square. When the failure is for 1, if the soil is cohesive soil, and second, if the soil is cohesionous soil. So you need to provide two sigma 1 value. Okay, one is for cohesive soil, another one is for cohesionous soil. Okay, so first of all, you need to understand the situations here. Okay, you have two samples. Okay, you actually have two samples, sample number 1 and sample number 2. Sample number 1, okay, the sigma 3 is equal to 100 kPa, okay, while the sigma 1 is equal to 288 kPa. Meanwhile, for sample number 2, okay, you prepare the identical specimens with the same moisture content and the same density. It's just that you subjected it to different confining pressure, okay, of 200 kPa. So the question asks you to find what is the major principal stress, okay, for two conditions of soil. Okay, what are the sigma 1? 1, if the soil is cohesive, okay, and number 2, if the soil is cohesionous. So you should know that, okay, theoretically, if the soil is cohesive, it means that it has the C value, while the friction angle will be assumed to be 0. On the other hand, if the soil is cohesionous soil, so it has no C value, but now the shear strength will be relies on the friction angle. Okay, so from here, you also know that the shear strength, okay, for cohesive soil will be equal to C. Okay, from the long or the complete molecular equation, we have C plus normal stress multiplied by tangent phi. Since friction angle is assumed to be 0, so tangent 0 will be 0. So the shear stress, shear strength will be equal to C. Okay, for soil, cohesionous soil, the shear strength would be normal stress multiplied by friction angle because you have no C value. Therefore, if you analyze it in Mohr Coulomb diagram, okay, this is your Mohr Coulomb diagram for cohesive soil. So the failure line, okay, for cohesive soil would be parallel to your normal stress axis, which is the x-axis, okay, because you only have a C value. Okay, on the other hand, for cohesionous soil, your Mohr Coulomb diagram would be like this. So your failure line will intersect to your origin, okay, in which that you only have the friction angle value. So if you look at these two diagrams, okay, you will know that, okay, for first sample, okay, with sigma 3 and sigma 1 that already provided, okay, so you can, if you plot the Mohr Coulomb or Mohr circle, Mohr circle, for the first circle, it will be something like this, okay, so this is your sigma 3 and this is your sigma 1, right? So your deviated stress here will be the difference between sigma 3 and sigma 1, which is the deviated stress at failure will be 188, right? 288 minus 100. So that is the difference between two principal stresses. Okay, and if you have another sample, which is sample number 2, okay, if you plot the same circle, okay, you plot another circle represents specimens number 2, which the sigma 3 is already given. It's 200, maybe it's somewhere here. Okay, so 200, they have to touch the same failure line. So this would be your new sigma 1 for second sample, represents cohesive soil. Okay, so you can get the value straight away if you solve these equations by graphical solution. Okay, for a condition number 2, which is the soil is cohesionless soil, okay, the same thing also, you can plot, okay, the first circle. Okay, let's say we know that sigma 3 is equal to 200, okay, 100. So let's say this is your 100 and this is your 288. So you have one circle, okay, represents sample number 1, and for sample number 2, okay, let's say it starts with 200 here. So you can do a try and error here, okay, to plot another circle and make sure that it has to touch the failure line. Because of why? Because these two samples will share the same shear strength parameters. So the new sigma 1 for soil with cohesionless types of soil can be also obtained by using a graphical solution, okay, as long as the circle, the second circle represents the second specimen will touch the same failure line. Because of why? You have to know that if you prepare identical specimens in which that the density and the moisture contents are consistent, are similar, therefore they are going to share the same shear strength parameters. So what are the shear strength parameters? The C and also the friction angle value, okay, depending on the type of soil. Okay, if the soil has only a C value, it means that the shear strength parameters only C, okay, and vice versa. Okay, the same thing if let's say you prepare another sample, okay, you prepare sample number 3, okay, subjected to a different combining pressure, let's say 250. So the same thing for cohesive soil, you will have another circle, okay, starting from 250 here. So they are going to touch the same failure line, okay, they are supposedly to touch the same failure line. The same thing also for cohesionless soil, okay, let's say your 250 is somewhere here, so you have to plot and they will touch the same failure line. All right, so this is the summary of the graphical solutions from the first equation just now that we already discussed. So you will got sigma 1 for cohesive soil equal to 388 kilonewton per meter square. For sigma 1 on cohesionless soil, you will get 580 kilonewton per meter square. So this is the full answer, okay, and also the solution based on the graphical solutions for the first equations, okay, in which that you will see that there is a two failure line here. This is the failure line, represents the cohesionless soil, okay, because the C is equal to 0 here, C is equal to 0, and it's only have a friction angle here. And another one is the failure lines for cohesive soil, okay, in which that it has no friction angle, okay, it only have C value here. So these two circle, okay, represents for cohesive soil, the sample number 1 and number 2 for cohesive soil, and another two circle here additional to that. So the same circle for this one, the same circle for sample number 1, but you have a different circle for sample number 2, okay, represents for cohesionless soil. In addition to graphical solution, if you choose to solve these equations by using an equation in which that we solve it by analytical solution, you can use the list of equations that I show you in the first few slides, in the first slides if I'm not mistaken. So there's like 6 equations. Okay, so you can choose to use those equations respectively to solve these equations, okay, or any equation related to shear strength. But you can also combine, okay, both, okay. Maybe halfway you solve it by graphical solution, but you will proceed with analytical equations. It doesn't matter, okay, it is up to you. So here I want to show you, if let's say you want to solve it by analytical equations, okay, rather than graphical solution. All right, so the same equations, okay, we know that you have the same sample just now. You have identical specimens, specimen number 1 and specimen number 2. Specimen number 1 with the sigma 3 equal to 100, sigma 1 is given 288. For sample number 2, sigma 3, okay, applied is 200, and it's asking you to find sigma 1, okay, for cohesive and also for cohesionless. Okay, so let's look at the cohesive soil first. We know that for cohesive soil, the friction angle is equal to 0, okay, in which that C is only, shear strength is only relies with the shear cohesion value. So shear strength is equal to C, okay. So what you can do is, okay, to calculate first the value of angle of failure, okay, by knowing the friction angle is equal to 0, so the angle of failure would be equal to 45 degrees. Why we have to find the value of angle of failure? Because we want to find what are the shear stress at failure, okay, by using these equations, okay. So we put all the informations for sample number 1, okay. Sigma 1 is equal to 188, sigma 3 is equal to 100, divided by 2, multiplied by sin 2 theta, okay. So you got 94 kilopascal. So if you plot the diagram, okay, you will see, you will have a circle, okay, for sample number 1, okay, starting with 100 kPa and 288 for major principal stress, and we know that the failure line will be parallel to your x-axis, okay, and this is your C value, okay. Since this is cohesive soil, so your shear stress at failure will be equal to C, okay. And to get sigma 1, okay, you can use, so to calculate a sigma 1 for second sample, okay, where the sigma 3 is subjected to 200 kPa, okay, we know that they will share the same failure criteria, in which that the failure strength parameters are similar, C value are similar. So the C value just now we got 94 kPa, which is equal to shear stress at failure for cohesive soil. So we can put into these equations, okay, to calculate sigma 1. Okay, sigma 3 is already given 200 kPa. Friction angle is equal to 0 because this is cohesive soil, okay. It has no friction angle value, assumed to be 0. So just put into these equations, calculate, and you got the answer. For cohesionless soil, okay, we know that the C is equal to 0. Therefore, if you plot a Mohr-Coulomb diagram, okay, for the first sample, we start with sigma 300, sigma 1 288. We know that the failure line will be something like this, okay, where the C is equal to 0, okay, C is equal to 0, and you only relies with the friction angle. So from graph, okay, this is where I told you that it can be a combinations between graphical and analytical solutions, okay, to speed up your process, okay, to speed up the process. Okay, we know that from this graph, when plotting the first Mohr circle, you will got value of shear stress at failure here and a normal stress corresponding to the shear stress at failure. So from that, you will got 80 kPa and 145 kPa. So the same thing also like a cohesive soil. You want to find out what are the sigma 1s, okay, with a 200 kPa of sigma 3, okay, which means that for the second identical specimens, okay, but you need to figure out first the parameters, okay, in these equations. So we already know the C will be equal to 0, okay, will be equal to 0 because it is cohesional soil, so this part can be excluded, so you leave it with only this, but you need to know first what are the friction angle value. Okay, so you can use a trigonometry, okay, because this is your friction angle, okay, so you can use up tangent, okay, shear stress at failure, okay, divide by normal stress, okay, so you got the friction angle value 29 degree. Put back into these equations, okay, calculate, the answer will be 576. So it will be a little bit difference from the first one, in which that we found, if I'm not mistaken, 580, okay, slightly different, but bear in mind you solve it by two different methods, okay, one is totally graphical solution, another one is a combination between graphical and analytical equations, so that will be slightly different but acceptable, within the acceptable range. Right, so now let's look at second example, okay, the information given here are the C value is 86 kPa, friction angle is 17, sigma 3 is 70, and sigma 1 is 346 kPa. So these two are known as principal stress, okay, these two value, okay, is really important for you if you want to plot a Mohr circle, because to get the Mohr circle you need to have sigma 1 and sigma 3 value, and the difference between these two are the deviated stress at failure, okay, at failure, okay, at failure. So the question asks you to calculate the angle of failure, shear stress at failure, and it's not normal, this is normal stress at failure. So you can choose whether you want to solve it by graphical solutions or analytical equations, okay, both you can do that. Okay, let's look at if you solve it by graphical solutions, okay, it's quite straightforward because everything is given there. Okay, so you have sigma 3 here and sigma 1 here. Okay, remember to plot a Mohr circle, the scale has to be consistent, okay. For example, that if you start with 50, so this will be 100, so it will be here 50, 100, 150, something like that, okay, so it has to be consistent. So let's say this is your 100 kPa and this is your 288 kPa. Oh, I'm sorry, the second question. Okay, for the second question, your sigma 3 is 70 here, sigma 1 is 346 kPa. Okay, and it's already given to you the C is 86 and friction angle is 76 at 17 degrees. So the C and phi value, okay, is important, okay, in order for you to plot the failure line. Okay, so the failure line has to follow the informations of the shear strength parameters. So let's say here is your 86, okay, let's say that is your 86 magnitude. So and the friction angle has to be 17, so the slope, okay, is 17 degree. So you take your protector, okay, this is your slope, which is 17 degrees, and this is your C, 86 kPa. So to get the shear stress at failure, normal stress at failure, and angle of failure, so from the diagram, so this is the point that tangents to your failure line. So here is your shear stress at failure, go down, this is your normal stress at failure. From here to here, this is your angle of failure. So quite straightforward from the graphical solution. But if you choose to solve it by analytical equations, okay, the same thing, the list of equations that I'll show you in the first slide, you can choose it and solve it. Okay, for example, like find the theta first, okay, before you calculate the shear stress at failure and normal stress at failure. Why? Because those two equations need the informations of angle of failure. So friction angle is already given. Okay, straight away using these equations, you got theta is equal to 53.5. And putting into these equations, okay, straight away, okay, you get the answer. Same thing also, this one you got the answer. If you compare your answer in graphical solutions and analytical equation, definitely it will be slightly different, okay, but again, I told you that it is within the acceptable range. So that's all. I really hope that you got an idea how to solve these questions with regards to shear strength by using both methods, graphical solutions and analytical equations, and you also know how to use the equations that we already discussed associated to shear strength parameters. Thank you very much. Assalamualaikum.